Well, I think we can get started. So hello, everyone. Welcome to Ask Seminars series. This is the last one in the spring semester, and this is John, the seminar coordinator. Together with me is Ms. Kathy Mednick, and she is our communication specialist. Kathy and I will be today's moderator, and we are excited to have our speaker, Professor Dara Entekhabi, joining us from MIT. Just so you know, then this seminar is being recorded and it will be later published on our YouTube channel. Please be free to ask questions. You can do so by raising your virtual hand and we will unmute you. You can also send us a message in the chat. Let me give a brief introduction about the speaker. Professor Dara Entekhabi received his BS and MS in geography from Clark University and PhD in Civil and Environmental Engineering from MIT. He is currently a professor with joint appointments in the Department of Civil and Environmental Engineering and the Department of Earth, Atmospheric, and Planetary Science at MIT. He is a science team lead for NASA's Soil Moisture Active Passive SMAP mission and was launched on January 31, 2015. Professor Entekhabi's research includes terrestrial remote sensing, data assimilation, and coupled land atmosphere system modeling. He is a fellow of AMS, AGU, and the IEEE. He is also a member of the National Academy of Engineering. Okay, so I will hand this over to Professor Entekhabi. Professor, please proceed.
Okay, first and foremost, thank you so much for the invitation to speak at your seminar series, and thank everyone for setting aside their a good chunk of their Monday afternoon to listen to this seminar. What I'm going to talk about is what has been done partially with a new data set, a satellite data set that became available since 2015 with this NASA SMAP mission, Soil Moisture Active Passive. And this is not just more data, it's a new type of data. So it should result in some new insights, hopefully. So what I'm going to talk about is basically address 4 questions very briefly that relate to the water cycle over the land branch of the water cycle. So the first question is really the fundamental one, is how are the 3 main metabolic cycles of the climate system, the water, energy, and carbon cycles, linked over land surfaces? So these 3 cycles, depending on how they're linked, will determine how perturbations from one propagates to the other. So it's quite important. It exists in every Earth system model out there. But the question is, can we observe these linkages without relying on models so that they become benchmark data sets for model behavior? Second is that as a new data type, can they spur a rethinking of the conceptual frameworks of our discipline, how water moves and is stored in the landscape? That's question 2. And question 3 is really the second part. The question is, what landscapes are most vulnerable to climate change? Are they necessarily the landscapes with the largest climate forcing, or is there something else that mediates it? And finally, much of the linkage between the water, energy, and carbon cycle occurs through vegetation. So we need to sort of focus on that as well, not just regard them as straws in the landscape. The question is, pulses of water availability spur some response in vegetation. How much of it is rehydration? How much of it is growth? And where and when and under what conditions? So these are the 4 questions, Q1 through Q4, that I'm going to be talking about. All of them sort of can be characterized under a general short title, Observed Water Exchange in the Soil-Plant Atmosphere Continuum. And I'm going to be presenting it, but really it's, as always, the work of a large team and collaborators. These are current and for students and former students. Actually, Andrew Feldman is a student who just graduated last week. Roosbe and Dan are current postdocs. Alex and Kagan have graduated and moved on with their careers. And Guido Salvucci is a longtime collaborator across the bridge at Boston University, so we work very closely together on all these topics. Isabel Trigo is a collaborator. Is not a former student postdoc, but is a longtime collaborator in Portugal in the Institute for Marine Studies. She's also the science lead for a geostationary satellite that we're going to be using a lot in the talk. So these are the sort of co-authors of various papers that I'm going to be drawing from in this talk. And instead of putting the citation on every single slide, it becomes a little cluttered. At the end, in the backup, I have a bibliography of all the papers used, so that's for the record. So the SMAP mission, the Soil Moisture Active Passive mission, launched in January 2015. Now we have 6+ years of observations. It's a wealth of data, and many surprises came out of it. Namely, the quality of the data was much more accurate than we had anticipated, and it allowed us to do stuff that we hadn't planned on doing, as you'll see in a second. It's a very low frequency microwave instrument, so it's in the 20 centimeter, about 20 centimeter wavelength, around 1.4 gigahertz. Originally, it had a radar, which was high resolution, but low sensitivity to surface conditions, and a radiometer, which is coarse resolution, but high sensitivity. And the plan was combining them to get an intermediate resolution and intermediate accuracy measurement. The radar failed very early on, but the radiometer is continuing to collect data, so it's a coarser resolution, so it's good for hydroclimatology, but quite accurate. The program level requirements include 5 science areas. These are basically the contract with NASA on what this mission should deliver on. These are all signed before launch. And there's basically in 2 groupings. One of them is sort of Earth system basic research questions in the top, and then application returns on the bottom, which I'm not going to talk about in this talk. Let me just briefly say about the applications. The applications are things such as drought monitoring, where agricultural drought is by definition a persistent deficit in soil moisture. Right now, or for decades, we've been modeling soil moisture in a soil moisture accounting to support drought. So now we have direct measurements. And then floods is, soil moisture is a strong condition for the transformation of precipitation and runoff. You can have the exact same precipitation event. Majority of it can become runoff, or none of it can become runoff, depending on what the soil moisture is. So it's essential in flood prediction. But in the science returns, let me just focus on the top sentence here. The number one goal, or the overarching goal, and the first science question that I put up at the very beginning, is to understand processes that link the terrestrial water, carbon, and energy cycles. So the key word is link. And one can think of it as the 3 main metabolic cycles of the Earth system, carbon, energy, and water, as gears in a clock. These gears turn together, and every single Earth system model has to have linkages between these 3 cycles embedded in it. It's never in one line of code. It's spread around in many lines of code across parameterizations. So how these things are linked in Earth system models is an emergent behavior, not a sort of coded behavior. But these closures are parameterized, and there's no benchmark data set or performance that they were required to adhere to in different Earth system modeling centers. So each one is different, and therefore this is a major source of uncertainty in climate models. To make this a little more quantitative, same diagram, let's take these three gears and just reduce them to three equations, just to see what the linkages are. Obviously, in a real Earth system model, this is spread across many, many lines of code and parameterizations. So the first one is the water balance. That's the change in soil moisture over a certain reservoir. Precipitation is the input, and evaporation is the output. We write evaporation as, or is the loss, as evaporative fraction, which is the fraction of latent heat to available energy. So it's a dimensionless number between 0 and 1, which multiplies available energy. So this is the evaporative loss, which is dominant for vertical exchanges. Then you have the heat exchange, which is the available energy minus the sum of latent heat flux and sensible heat flux, which together are the turbulent fluxes. So this is standard energy balance. And then we can sort of characterize the biomass, the carbon cycle, as the change in the sort of the biomass content of the surface as evaporation times the water use efficiency, which is just the ratio of how much the carbon dioxide and water vapor exchange occurs in the photosynthetic process. And then there's a sort of a senescence term for vegetation. So what's clear from this picture is that this function, evaporative fraction, is what links these three cycles together. And water use efficiency is an additional multiplicative factor for the carbon. So these evaporative fraction and water use efficiency are what are parameterized, and they depend on the state variable of the system, which is the water in the landscape. So if the water is limiting, then evaporation goes down, and vegetation respond to stress and how much water there is in the landscape. So these are the closure functions that each modeling group has their own approach to. And if they're not consistent or they're not accurate, then the way these three cycles are linked and perturbations in one translates or propagates to other is going to be different among models, hence the uncertainty. What is the state of affairs? So let's just look at this diagnostic evaporative fraction versus soil moisture for 6 Earth system models. This is a historical run for 6 SMAP 5 models. Doesn't matter which one's what, the question is how different are they? This is done for this piece of real estate over central US. And what is clear is that the dynamic range of the variables and even their slopes and behavior is very different for the different models. If you look at the carbon exchange, it's even more divergent between them. So this, to me, is the statement of the problem. There's divergent approaches to the parameterization in each model, which leads to uncertainty. Again, this is the 3 main metabolic cycles of the Earth system. So number 1, there's divergent approaches. Number 2 is that our traditional way of assuming that if in a parameterization we link individual pieces that are good, that the end parameterization is going to be good, does not necessarily work. The pieces don't add up together necessarily. And also what we really need is a benchmark observational data set for this kind of behaviors for models. So what we need to do is to come up with a, benchmark data sets is to have evaporative fraction observed, soil moisture observed from independent sources so that we can create a benchmark data set. And same thing here. So we have to have the X and the Y axis independently observed and not part of any model or a simulation system. So the approach is for the X axis, soil moisture, is to use SMAP. For the energy fluxes, we use the weather stations over the US and as a method for estimating energy balance components, ETREC, citation here. And for the carbon flux, we're going to use solar-induced fluorescence from two satellites, NASA OCO2 and GOM2. So this is the carbon flux, energy flux, and the surface soil moisture state. And from that, we get these sort of benchmark behaviors. This is for different regions in the US. Evaporative fraction versus soil moisture, what we clearly see is that there's a two-regime behavior. When the soil is adequately wet, there's the energy-limited evaporation regime, where energy is the rate-limiting factor. And then you have, across the threshold, a water-limited regime where the soil moisture reduces the evaporation rate. For the carbon flux, we see the same two regime behavior, but for different ecosystems, because there's different types of plants and density of plants, the plateau is different. It doesn't all plateau to the same number. So this is a observationally based benchmark for these two main closure functions between the water range and carbon cycle over land. We can take the carbon flux and turn it into a water use efficiency. So this is the landscape water use efficiency, that's per unit area of land. This is sort of normalized for the vegetation fraction. So this is leaf level water use efficiency, which we are mostly used to looking at. It's got a very strong hyperbolic behavior, and this is just a close-up from 0 to 0.5 of the same figure on the right. So it's a very strong hyperbolic behavior. What this says is that as the plants become stressed with water stress, it becomes much more efficient in exchanging water for carbon, and it assimilates a lot more efficiently at low soil moisture levels. Now, this has been observed in chambers in laboratories where you take plants, put them in a chamber, stress them, and measure the carbon water exchange as a function of what you're stressing them. There's lots and lots of these studies in physiological plant physiology journals. Here's just one example. And they also show this hyperbolic behavior, but this is now in a mapped global setting rather than a chamber. So let's go on to question number 2, is that here we have a new data type, surface soil moisture, which is again the state variable of the landscape water balance. Does the new data type sort of inspire or spur a rethinking of our conceptual frameworks for landscape water balance and hydrology? Again, a new data type makes you look at the problem from a different angle, and that should lead to some serious questions about what's going on. So one thing to note is that soil moisture itself, the state variable, really in itself does not have a scientific meaning and value. But where its value comes in is how it controls and activates hydrologic processes. And as we've seen before until now, that there's different evaporation regimes, for instance, separated by a soil moisture threshold. How does it mark or activate different hydrologic regime as it fluctuates? And that's what really matters. So let's see how we can do that. Here's again now a time series an example time series of soil moisture at a location, I believe it's somewhere in Oklahoma, that comes out of SMAP. So this is just 1 pixel. This is the time series of the soil moisture over a few months. And it's just an example to show that when you have a precipitation event, soil moisture jumps up. Then you have a period of dry down where the water drains out of the landscape and evaporates. Then there's precipitation event again. Then there's a long dry down, another event. So you have these sort of punctual increases in soil moisture due to precipitation, and then these dry downs due to evaporation and drainage. Now, one thing one should not do with a time series is take its derivative, because that just amplifies noise. But we did it anyways, and it turns out that the signal to noise ratio was such that there was still a lot of signal left. So here's an example of taking the time derivative of this signal over this period. So this is change in soil moisture. Whenever there's a rain event, like here, there's a big and singular increase in soil moisture. Rain occurs over very compact periods of time. But then when you have dry downs, you have these negative increments, and generally they seem to have very high rates at the beginning and then slowly decay over time. So you see these sort of exponential decays in the interstorm period. Now, if this time series is statistically stationary, meaning that the landscape is not indefinitely gaining or losing water, then the average of the blue and the average of the red should equal over time. That's statistical stationarity. It just means it's going up and down around the climatology. And if we plot the probability density function of the red and the blue, you get these two probability density functions. And as statistically stationarity implies, their means are the same. They have to be. But their distributions around that mean are quite different. Can we extract information about hydrologic processes from that difference in the distributions, from the asymmetry among them? So let's go back to the time series and sort of dig a little deeper. Here's time series again, now with precipitation also plotted to show these increases. So here's an example of a very long dry down. Here's another dry down. The reds are identified periods of continuous decrease in soil moisture. If I take any one of these, so this is just one of these dry down events. After a pulse of rain, soil moisture is quite high. This is soil moisture. This is over time. And very quickly, soil moisture is reduced to this level, which is called the field capacity. It's an old soil physics definition. It's a soil moisture level below which gravity is not adequate enough force to draw water out of a soil column. So it's an energetic definition. So this field capacity, anything above it, it's gravity drainage, and it's quite efficient and quite fast. So you see this rapid decrease. Then once you hit field capacity, the drainage process stops. And evaporation now takes over as the dominant hydrologic process. So you have a shift in processes. When the soil is still adequately wet, the evaporation is energy limited, like we saw before. So the evaporation rate is a constant. It's equal to the available energy or potential evaporation. So the rate of dry down is linear until you hit a threshold in which you switch yet to another hydrologic regime, which is the water limited regime. Now soil moisture exerts control on the loss rate, and the drier it gets, the more control it exerts with basically capillary and hygroscopic storage of water in the soil. And its reduction rate becomes slower and slower. So these three regimes, the loss rate, which is the slope here, can be plotted conceptually here. So at very high soil moisture, this regime, until you hit the field capacity, the drainage is very strong. Then you hit a sort of the energy limited stage 1 evaporation, where the loss is potential evaporation, and then the soil limited evaporation. So what are these loss rates? These loss rates are just the increment change in soil moisture over the elapsed time. And this plot is versus soil moisture as the independent variable. So we can reconstruct this curve using this data alone by taking a conditional expectation of the change in soil moisture during dry downs. So here you see an example, for this example, of the loss rate, and at least two of the regimes are dominant, evident here. So if we do this, sorry, for the US, you could do it over the globe, but we do it over the US so you can see what's going on rather than a postage stamp of the entire globe. And then we can create diagnostics, like what percentage of time is the landscape in the hydrologic regime where it's water limited? What fraction of time is the landscape in a wholly different hydrologic regime, which is energy limited? And what fraction of time is it in the drainage dominated regime? So the three regimes just identified before. So we see some patterns, such as one would expect, in the western half of the US is more water limited, more energy limited in these regions, and then drainage dominated in these regions. Now, here's something I actually found yesterday, which is from this source. It's a map, county by county, using ground surveys of what percentage of each county has so-called tile drainage. Tile drainage is a hydraulic intervention with the landscape for farming purposes, where horizontal drains are dug a few tens of centimeters, meters below the surface, that drain the landscape into ditches in order to make the soil suitable for agriculture, or else it would be waterlogged. So these regions have a fairly high percentage of tile drainage, which kind of is reminiscent of the same region that is, from just SMAP data alone, designated as drainage dominated. I can't say that there's a causal link between these two, but it is a fairly curious correspondence between two entirely different data sets, one satellite and one ground survey of a certain condition. Now, if we take these same three maps, we can then classify them into which of the regimes are present. And the reason why I do this is that this is not just a map of something that we could have guessed before, that the West is water limited, the East is energy limited. But these things move from year to year, from week to week, month to month. And we can track those movements between different years in this example. And there's a wealth of information in looking at how these things evolve over time. I'm just giving you a summary. So there's regions which go in and out of one regime to the next, depending on the year, come in and out. These boundaries, the green, dark green lines, are for this curve as benchmark. So there's a lot we can learn about which hydrologic processes are dominant, when and where. We go back to this same thing. Wouldn't it be nice that this loss, if it were not just one loss combining the three regimes, that we could separate it between evaporation and drainage. So in order to do that, let's just pose some functional forms for these, evaporation and drainage, but be very flexible. Don't let it become a model. So for evaporation, you have a two-regime function. This is just a function that has a parameter A and B, which allows it to be anywhere in this domain. It can go up and down, it can go left and right. So A and B just say, give me a two-regime, but I won't impose where these transition and sills are. Same thing with drainage. Drainage, this is sort of equivalent to hydraulic conductivity, unsaturated hydraulic conductivity on a unit gradient forcing. It's a hyperbolic function, and it says, give me a C and a D that could be anywhere in this space, and C and D are free to vary. So here we are, we get a cost function. We say fit the brightness temperature, which is the soil moisture essentially, and adjoin those loss functions in here and estimate A, B, C, and D. So this is in a sense fitting a land surface model, but inverting it completely, saying that I'm not telling you what the precipitation and radiation fluxes are. I'm just telling you what the state variable dynamics are, and fit it the best you can using that A, B, C, and D. And what you get out of this variational scheme is the total loss, the black line, partitioned into drainage, the blue, and evaporation, the green. So drainage occurs during very wet events, and then it's non-existent. Evaporation is the rest. So again, this is a land surface model, typical land surface model, which the input is precipitation and radiation and wind, and output is the fluxes. That's all we care about. We don't care what the soil moisture values are. We don't compare it across models. This is turning the problem inside out. We observe the state variable and its dynamics and try to track it the best we can and, in a sense, identify the model. Here's the parameters A, B, and C, and D, which doesn't really matter. We're not interested in those. What we're interested in is the evaporation and the drainage climatology that comes out of it. And this, again, I dug up yesterday from a USGS source, is the map of drainage based upon models that USGS operates. Unfortunately, I didn't have time to put it all in the same color scale and reduce it so it's more visible, but the range of numbers are similar, and some features like in the Northwest seems to show up. Some features in the Appalachians seem to show up. The high values here are snow dominated, so we're not going to get those, obviously. And just for completeness, whatever Ameriflux stations there were in the US, we threw together for a comparison, and USGS stream flow for comparison when you average it over a basin. It's apples and oranges. These are point measurements. These are spatial support measurements. These are, again, spatial support measurements. These are basins with hydraulic structures, dams and levees and all sorts of stuff in between. But one thing that comes out is that the two are unbiased with respect to one another. The one-to-one line goes to 0 and 1. And the explained variance is around 70% in both cases. And now we can look at the partitioning. What fraction of precipitation is drainage and evaporation in each of these cases? And you can think of this conceptualization of what's happening in the landscape as these loss functions. And this is the time series of soil moisture, and this is the marginal distribution of soil moisture. So really, the landscape response is a derived distribution of these loss functions with this marginal probability density function. In this case, 3/4 is evaporation, 1/4 is drainage. So this is, I just turned the PDF on its side to show you that this is really a derived distribution. Now we can sort of test the amount of nonlinearity in the system. What if we just increase the precipitation by 25% or decrease it by 25%? Does the partitionings also change by 25%? They don't, because this derived distribution is over nonlinear processes. So if you shift it left and right, it triggers different amounts of each of these loss functions. So there is strong nonlinearity in the response. So this is one conclusion. Now, this is just artificially changing precipitation by a certain percentage over time. We actually know the precipitation over time going back to 1948. So we can now look at the year-to-year variations in the partitioning over the entire US and its basins. Let me jump. The next topic very quickly is this issue of vulnerability to climate change. Land surface response to variability to climate forcing is obviously positive, but are all landscapes the same slope, the same vulnerability? Are some landscapes more vulnerable to climate forcing than others? And what are the physical mechanisms? So this is just a cartoon. Here's what we want to explain. This is precipitation interannual variability over Africa. And we want to see how that affects things like evaporation, because that's the key variable in the water, energy, and carbon cycle linkage, as we saw before. And what is the relationship between these two? Obviously, we don't have evaporation unless we rely on models, which we don't want to do. We want to be purely observational. So what proxy can we use for the water, energy, and carbon cycle processes? Now, this problem is inspired by the work of Peter Eagleson, who was an emeritus faculty at MIT, passed away just earlier this year, in a remarkable 7 series of papers in water resource research. He showed that if you know the statistics of storms, arrival times as a Poisson process, intensity and duration, and you know what's happening at the weather scale during one dry down, during just an interstorm period, you can, combining these two, derive the interannual variability of the water on the landscape, the yield in this case. So this is the cumulative density function, and this is the yield over the landscape. So he showed that climate scale variability, interannual variability, can be deduced from the statistics of storms, and an intrinsic landscape response that gets established during the weather events. So we want to follow the same sort of outline. So we don't have evaporation, but we do have surface temperature measurements. And if I plot the diurnal amplitude of the surface temperature, which is going to get affected a lot if the surface energy balance is water limited or energy limited, then if I plot those for these landscapes and climates, you do see the energy limited regime where there's no response, soil moisture is not engaged in energy balance, and then a threshold where it suddenly becomes engaged, the water limited regime. So at least we can detect the strength and the threshold. And this is not just fantasy. We can look at a flux net station where this same diurnal temperature amplitude is plotted. This looks the same as on the right. And here's the evaporative fraction as determined by the eddy flux measurements over the site. So the two regimes are present. Now, where do we get the diurnal amplitude for that? You need to go to geostationary satellites, obviously. And there is a European Meteosat second generation instrument that is sitting on the equator over Africa. So the best data from it is actually over Africa. So it's a wealth of information. And our Isabel Trigo, our Portuguese colleague, is the science team lead for that. So we have these two data sets that we can now combine. This is the threshold soil moisture as estimated from those curves. I won't dwell on it. This is the fraction of time in the water limited evaporation regime that we can deduce from the soil moisture variables alone. And here's the conceptual model. Again, the diurnal temperature amplitude, like we saw before, there's a threshold, there's the energy limited, insensitive to soil moisture, and the water limited, which is very sensitive to soil moisture. And again, it's a problem of derived distribution. This is the PDF of soil moisture, and it moves left and right year to year, and it determines the landscape response. So if your PDF is all in here, you're not going to get much of a response. And if you transition between the two a lot, that means that on climate scale, you're going to be very sensitive as well. So this was the transformation that we were questioning. How much of the interannual variability in precipitation is translated into surface flux variability, or put it the other way, the surface flux variability, how much of it is derived from precipitation forcing? And if you plot that transformation for different levels of the regime dominance, the weather regime dominance, you get a clear signal that the slope keeps going up. So it's all a matter of where this PDF is relative to this threshold, and how does this slope in the water limited regime, what is the intrinsic slope for that landscape unit. The last thing, very quickly, it will take less than a few minutes, is the fourth question. In the water, energy, and carbon cycles, the link is through evapotranspiration, where plants are the critical factor. So how do plants respond to these precipitation events over the land surface? And what do we know about it based upon, again, pure observations? So during dry downs, there's these pulses of rain that soil moisture goes down, and the plant is using that up. The question is, how is it using it? And the basic point is that the water exchange, due to these pulses of water resource availability, is very much dominated by the when you are and where you are in this dry down. And it works in the reverse direction as well. The carbon flux is going to be affected by the intermittency of rainfall. Therefore, trying to understand the water balance or the carbon balance, namely the carbon balance, based upon time averages like monthly precipitation, is going to miss all this dynamics. So with SMAP, we not only can get the volumetric water in the soil, or the water content, volumetric water content in the soil in these units. Here's an example of some climatology. We can also infer a similar quantity of how much water there is in the plant, because the signal is attenuated from the surface to the plant. So we have simultaneous fields every 2 to 3 days at about 40 kilometer resolution, evolution of these two fields together. So what can we say about soil vegetation, atmospheric continuum, and the water movement through it? So again, we focus on dry downs. The same blue time series are the soil moisture dry downs with red dots, with soil moisture time series with the red dots as the dry downs. But now we have vegetation water content in green. If I isolate a few of these dry downs just to look at them closely, here's one dry down, soil moisture by definition going down, and then sometimes vegetation water content goes down, sometimes it goes up. So obviously it depends on the initial condition of soil moisture. In order to see how these two variables relate to one another, conditioned on their respective states, we have to go to a phase diagram, meaning take the time variable out and look at the evolution of soil moisture and volumetric vegetation water content. So this is, as you go from right to left, is a dry down. So it's pretty noisy for this little short time series. But if I look at these same blocks as you saw before, areas of similar climate and vegetation, with satellite data over 6 years, you get a lot of dry downs. So tens of thousands of dry downs. So they all overlap, so there's not much to see. But if we take blocks of the figure on the left and just average them so that all the noodles that appear in a box track them, we get a picture like this. So this is the phase diagram of water movement in the soil and vegetation. When the soil is wet, right after a storm, the slope is very large. There's a lot of water uptake. Vegetation water content goes up. And then at a certain threshold, there's a crash. The plant just starts losing water at a very rapid phase. And that behavior is different for different vegetation types. And again, I'm just showing examples of these. There's a wealth of information to be learned about vegetation response to water stress and what different vegetation types are doing. So for instance, we look at the slope, the rate of water uptake. We look at the threshold where the crash occurs. In most models, this is set at 1.5 megapascals, but actually there's a distribution of it. And finally, if we bring the time element back, there's a lag. This is a wetting event. The soil moisture goes down right after the pulse of rain, but the vegetation actually peaks sometime later. The question is this rehydration or is it growth? Different vegetation types will have different behavior. So one thing we did was go back to severity, because this is an optical instrument. We have leaf area index around the clock. So we can look at the change in the leaf area index. This is an indication of growth, not rehydration. And we see that there are some characteristic events that are mostly growth and those that are not. So this is distinguishing rehydration and growth. Again, this is just tip of the iceberg of results. So let me conclude the 4 questions we posed at the very beginning: linkage, rethinking the conceptual framework, vulnerability to climate change, vegetation response to pulses of water. So for the first one, we can say that we've arrived at a observation only, no models. Because if you use models, you're lifting yourself with your own bootstraps. Linkage between the water and energy and the water and carbon cycles that link the 3 cycles and should be benchmarks for these emergent behavior in Earth system models. Second is that we conceptualize, using the new data set on the state variable, we conceptualize now the hydrologic response and the partitioning of precipitation into evaporation and drainage under different seasons, conditions, locations as really a derived distribution problem, and that the response function can be estimated from the data alone, not models. Which regions are most vulnerable to climate change? We find that the position of the soil moisture probability density function with respect to that threshold and the response function are key, and those behaviors are established at weather scale, and that you can't average them up across intermittency. You really need to take care of intermittency. And how do vegetation respond to pulses of water? Rehydration and growth response are widespread beyond drylands, and intermittency can affect not only the water exchange, but the net carbon balance. So you can have the same precipitation in a climate change scenario, but if the intermittency changes, you have a different carbon balance. So I'll leave this slide as the conclusion. As I promised, here's the bibliography at the end, which is, for the record, available. Thank you.
Thank you, Professor. If anyone has any questions for the speaker, you can raise your virtual hand by opening the attendee panel and clicking the hand icon, and I will unmute you. Or you can put something in the chat, just ask to be unmuted. I can do that as well.
Unfortunately, with shared screen, I don't see the chat box. So if
Oh yeah, I can let you know if anyone is chatting. Oh, here we go. We got a question from Mike Evans. Mike, you're unmuted.
Hi, yep, thank you so much for this talk. I was wondering how you ground truth the estimates of the plant moisture.
That is the best question. That we really don't have an equivalent measurement of that quantity on the ground. It was not one of those. No, really, there's SAP flux measurements. There's very occasional destructive measurements, but no direct measurements. So really, the way we can assess it, not validate it, is in use cases, in examples of their, do we see the behavior we expect? But on top of that, we have made that the target, the goal of the next SMAP field experiment, airborne field experiment, which was delayed twice due to COVID, but it's going to happen in 2022. So we have a airborne field experiments with ground truthing, with lots of ecological measurements, plant measurements, coming up in the summer of 2022. That's really the best we can do. There is no network of VWC.
Thank you. Oh, there is a text question that was just sent to me. What is the follow-up for SMAP? What can we learn from SMAP and improve future missions?
I guess what can we learn in terms of implementation of the project is a whole different thing. That's not my, I think what you're asking is that what happens after the SMAP mission goes away? Is there a follow-on for continuity? Right now, SMOS and SMAP, the European mission, L-band radiometry mission, is called SMOS. Both of them are aging. SMAP is 6 years old. SMOS is, I think, over 10 years old. And at some point, they'll go away. Follow-up missions, or there's a number of Earth Venture type missions being considered, but the most promising one in terms of continuity is the SIMMER mission. Actually, tomorrow is a 3-day conference. It's a European Union Copernicus mission. It's an operational mission around 2027. It's a multi-channel microwave, L-band, C-band, X-band, Ka and Ku. Multi-channel. It uses the same antenna as SMAP, and it's multi-channels, and it's got a very wide swath. So in that sense, it's really, really nice. But it doesn't have an active system on it. So its resolution is similar to SMAP, but the revisit is a lot more, but it has multiple channels. And also, I believe there's a joint mission between China and France that's also being discussed, L-band continuity.
Thank you. We also have a raised hand from Jicheng Liu. Jicheng, you're unmuted.
Hi, Dana. This is Jason Liu from Nest Star. And it's so impressive that you guys did such a wonderful job on the dry down process of soil moisture. And it seems to me that we are very, very close to a stage that we could actually characterize all the dry down process for all different situations. I'm just wondering if there's any plan to implement all this process into the actual SMAP soil moisture retrieval algorithm to just do some kind of adjustments, or as a guide of it's actually drying down. If you predict that so much is going up, that's wrong. So you can implement this process into the retrieval algorithm so we can have a better retrieval.
Yeah.
Do you expect that?
Yeah, I mean, both, remember the evaporative fraction and water use efficiency versus soil moisture curves at the very beginning. And
Yeah.
in towards the middle, when we talked about evaporation and drainage curves versus soil moisture, those are diagnostics, but based upon observations alone. And land surface models that are used in data assimilation or numerical weather prediction or earth system modeling, they will still need to continue to parameterize all the processes individually, like, you know, every detail that we deal with these days. But in aggregate, they will have an emergent behavior, which are those benchmarks. So I'm hoping that one thing we can do is use such approaches, not necessarily this exact one, but such approaches, to come up with accepted benchmarks for those emergent behavior in our models. I'm not saying throw our models out the window. We can't. We need to continue what we're doing. But we need to have accepted benchmarks for our model performances. So if the way it can help SMAP products is, for instance, in our level 4 data assimilation products, that's the result of a land surface model and observations. So that's just one use case of a model sort of benefiting from a benchmark. But I hope we go far beyond that and really look at our land surface modeling with a common target.
Okay, thank you.
Thank you. I do have one question from Jifu Yin, who's been waiting, and he says sorry he doesn't have a microphone. Jifu asks, it seems water, energy, and drainage limited classifications cannot fully cover the CONUS domain. So what is the classification for the remaining areas?
I hadn't, I don't want to flip back, but one thing that we filtered the data for frozen ground, for one, because the retrieval of soil moisture is just not possible under those conditions. We also filter it for extreme topography. And, so, if it's really mountainous. And we don't filter, but we should, but we flag for two things. One is we still retrieve where there's snow water affecting hydrologic processes, and we still retrieve but flag where there's very dense vegetation, like, so that the attenuations of the signal is such that the signal to noise ratio is just unacceptable. Frozen ground and high topography is out. There's just nothing, and also lots of water bodies. But the snow and the vegetation we keep, but interpret cautiously because there's information in there. You want to see where the breakdown boundaries are. So if there's anything missing, it's because of those kind of factors.
Thank you. Professor, do you have time for another question? I know you said you had to leave. Okay. So I do have a question from Yu Lin Feng. She asks, what's the best temporal and spatial resolution to derive the hydrologic loss functions? Does hydraulic redistribution matter in this type of loss function classification?
Yes, that's a really good and insightful question. The transitions between the regimes and also the duration of the drainage regime are oftentimes less than the time between SMAP revisit measurements. So that's an issue. And with Simmer, that is alleviated quite a bit. We actually use both AM and PM to sort of have our revisit times, essentially. The drainage regime can last less than a day to a day and a half. And the transition between the water limited and energy limited can happen in a matter of a few days too. So the more temporal visits you have, the more you can extract out of those. But since we're looking at 6 years of data, you randomly sort of sample those regimes, but it's sort of a very noisy way of doing it. If you combine SMAP and SMOS, then that's daily measurements. That's really nice, but that's a lot of effort.
Thank you. And this is the last question that I have. The soil moisture has also been retrieved by GNSS reflection. What is the difference compared to SMAP?
Okay, the GNS reflection, a prime example of that is the Cygnus mission, which is a constellation of receivers that get GPS signals, reflections off the surface. That is coming along. We're working closely with them to, for the in situ sites that, and also comparison sites. It would be great because that's a very good way of getting measurements from a radar system that you don't send the receiver up. There's lots of research yet to be done on what the reflections represent. The dual Doppler measurements that are made depend on topography, slope, aspect, and all that. And those are track measurements, they're not mapping measurements. I'm hoping that actually the best data comes from combining the two rather than one replacing the other. I think that's where the opportunity is. And also, the more information we have, the better we can constrain the vegetation and roughness, which are really sources of uncertainty in the retrievals.
Thank you. That's all the questions that I have. So unless there's a last minute one. Thank you, Professor, for coming and giving us this great talk. Thank you, everyone else, for attending and for asking questions and participating. This is the last seminar of our spring semester. So thanks, everybody. I'll see you next semester. Maybe we'll have some summer ones. But
thank you for your patience and interest. Thanks.
Yeah, of course. And thanks for joining us today. Have a good day, everybody.
Bye.
Thank you, Professor. We will send you the video recording after we get it. Thank you so much.
Okay, thank you.